Hello. Hello. The square tells you what you should do, right? You should use your clicker to press the button corresponding to your answer to this question about this triangle. By the way, oh no. All right, now it works. I've answered the question. So again, read, think, press. Yeah, and by the way, if you want to try, it's not easy, well, at least not as easy as it seems, to generate many questions, many answers, which might have at least some kind of a sense. So a simple yes or no answer. And the no is the right answer. Of course, seven is even better. One 16376. Yeah. So, what did I want? Yeah, here. Just to remind to all of us, even if the hypotenuse is equal to 5 meters, there is infinite number of triangles which might have exactly the same hypotenuse. This is only one of many, right? But for example, I can draw another line like this, and I can draw a perpendicular to this line, 90 degrees. So this new triangle has the same hypotenuse, but clearly sides are different. So what we should look for is the angles. The angle is the more important feature than the length of the hypotenuse. If we have a was it 30? Yeah. Well, it looks like 60. If we have a triangle like that, 30 degrees, and that's 90, that's automatically 60. And if this is 5 meters, we can easily calculate each length. For example, this is supposed to be 2.5, right? Hypotenuse times the sine of 30. That's supposed to be 5 times cosine of 30, which is, again, not 3, not 4. Oops. Déjà vu. So, geometry. Let's go back to physics. 2 blocks. One is hanging down on a string, another is on the incline, and we need to calculate tension, acceleration, anything we want to. First question, what is the mass of this weight? What is the number? 1 kilogram? Sounds a simple question, but imagine how much work our brain should do. Read, then correspond, fine, that's 3, that's not 3, not 3, 1, see? Pattern recognition. 1 kilogram. But more important question is, how many regimes, how many possible situations could be happening in a case like that? If you had it set up at home, why not? All you need is 2 weights, a pulley, a string, and some kind of an incline. What could have happened? So how do we count? We count, well, 1, yeah. So there is only 1 possible regime. 2, there are only 2 possible regimes or situations or cases which we can observe happening in this case. 3, 4, well, I don't know. So this is what I want to ask you. That's a physical question. Please. What do you think? Use your imagination, common sense, life experience, guts, intuition, money, offering to your friend for an answer. Anything works. Well, by now, you know what you want to press, so you don't have to look at it. Plus, by now, you should have a copy of this picture in your notes anyway, right? So, you used to be over there. What happened? You should have buy a ticket first. So what did you say? What number? No, I don't like that. What did you say? What's your answer? What did you say? 3. I like 3 better because, well, if we ask what might happen, first question, the first possible answer always is nothing. And nothing would mean we let them go and they don't. That's what we call equilibrium in physics, rest. That's one possible option. Well, another possible option is what? They start moving, and we can stop counting. So 2 is a reasonable answer. But there is a little bit more reasonable answer. If we dig deeper, if it starts moving, well, this can happen. The heavy slides down and another Y goes up. Or if it starts moving, this might happen. If we look at them moving. So 3 regimes is also a reasonable number. But if we dig deeper, there is another reasonable number. If it starts moving, we also can ask a question, how? And we have 2 possible answers for that question. Well, normally it's either with constant velocity, which means no acceleration, or with constant acceleration, which means, well, speeding up or slowing down. So to each picture with the motion, we can add 2 options. The acceleration is 0, which means velocity remains constant. Another option, same objects, same arrows, but now the acceleration is not 0, the velocity is not constant. And of course, same here. Now this is moving that way, this is moving this way, and here the acceleration is 0, velocity is constant, and here the acceleration is not 0 anymore, and the velocity is not constant anymore, so 5. And you said all of them, and even more. Why is it happening always when I press this? So, of course, we have to solve the problem to know what is exactly happening. So, we can use our imagination to see how parameters might work together. Imagine that we are changing the angle first. So if I make it more and more horizontal, eventually, what should happen? Well, we have solved the problem when the surface was horizontal. In that situation, this weight getting down must start moving down, and the one which becomes horizontally must start moving to the right. That's one possible situation. If we make this angle smaller and smaller, 15, 20, eventually we go back to the Atwood's machine, yesterday's class. And in that situation, the heavy one definitely will be moving down, the light one definitely will be moving up. So the angle might matter. But another possibility is, well, we can change the mass of that hanging down weight. For example, we can cut it out, cut it completely, which means mass is 0, or almost 0. What's going to happen? Well, of course, in that case, 3 kilogram weight will be sliding down the ramp. But if we make it heavier and heavier and heavier and heavier, more and more mass, eventually it wins over. And in that case, the 3 kilogram weight starts sliding up the ramp. Clearly, there has to be a critical value for everything. There is a critical value for the angle. There is a critical value for that mass. When that critical value is reached, that should be equilibrium. So, the first question we should answer is, what is that critical mass we should attach to that string in order to make the system in equilibrium? So, we attach it, we release it, nothing at rest. Well, what does equilibrium mean? We said it several times. It must mean something specific. What does it mean? Absolutely right. Net force must be equal to 0. Well, in this situation, net force acting on the first object has to be equal to 0. Net force acting on the second object must be equal to 0. So here we have m times g acting down because of the gravity and tension acting up because of the string. Here we have another tension which points differently but has exactly the same magnitude. And well, what do we have here? We have normal force. And we have a force of gravity which points, well, it points straight down. But for that particular block, that direction is not really convenient. So instead of using the actual force of gravity, we always can use two components of it. This is what we used to call mg perpendicular because it's perpendicular to the surface. And this is what we used to call mg parallel because it's parallel to the surface. So that's an equivalent free body diagram. And of course, the normal force should cancel mg perpendicular, which is times g times cosine of this angle or the incline. And of course, net force equals 0. The magnitude of the tension should be equal to mg. Oops, see, I said parallel. And mg parallel, as we know it now, is supposed to be equal to m times g times the sine of this angle. And this is the Newton's second law for this subject. And Newton's second law for this subject, well, tells us that this product, the force of gravity acting on this weight, must be equal to the magnitude of the tension. Otherwise, they couldn't cancel each other. Any questions on this kind of a reasoning? So tension, same variable, same value. If we combine these two equations together, this product, the critical mass of the small weight times g, should be equal to this product, the mass of the big box times g times sine of theta. Cancel g, cancel g. So the critical mass should be equal to 3 kilograms times, what is sine of 30 equal to? And you see how much time you spent to calculate it. So it might save time to remember values for simple angles. Sine of 30, a half. Cosine of 60, a half. Tangent of 45, 1. So times 0.5, 1.5. That's a critical mass. If we attach exactly 1.5 kilograms and we release it, nothing happens. It remains at rest. In fact, what's going to happen if I give it a slight push? What do you think? So if I attach the critical mass and I make it into the motion, give it a slight push, what should happen? Nothing. Moves with constant velocity, moves with constant acceleration, not equal to 0. The answer doesn't depend on geometry of this problem. Equilibrium is equilibrium. So exactly same experiment we can do right now using the Atwood's machine. Bless you. You're welcome. These two weights are in equilibrium. It's because if I have 100 grams here, the critical mass for this weight is also 100 grams. So the question is, if I give it a slight push, what's going to be happening? Doesn't matter. I'll stop it later. So you just compare what you thought with what you see. Oops. So what was happening after I gave it a push? it was moving first. Now, of course, when I touched it, I broke the balance for the moment. The net force was not zero anymore. But when I stopped touching it after that, the net force acting on this weight has to be equal to zero, nothing else. Same here. So they should both travel with zero acceleration, which means constant velocity. If I had no friction at all here, friction, of course, is acting here, but if I had no friction, well, and if I had it very, very tall and long, they would travel with constant velocity, well, until it hits the pulley. That's it. This question is about understanding how Newton's law works. All right. You see, that's a pretty good percentage of the correct answers. I'm glad I asked this question. No, close this. Well, okay. We know now that the critical mass equals 1.5 kilograms, but the actual mass attached to it is equal to 1 kilogram. So this is the actual situation. 3 kilograms, 1 kilogram. 1 kilogram is less than 1.5 kilograms. Any questions on that? So what should we observe? What kind of a motion? This one should be moving up, and this one should be moving down the ramp. If instead of having 1 kilogram, I would have attached 2 kilogram weight, they would move in opposite directions. That's it. And now, of course, well, everything is exactly the same as we said before. We just have to set each net force not to zero, but to m times acceleration. They both have the same magnitude of the acceleration for the both objects is the same. Direction is different, but the magnitude is the same because the string doesn't stretch, has a fixed length. So Newton's law number 1, Newton's law number 2. Well, x, y. This is the set of axes the most convenient to be used for the first object, for the little guy. M, G, tension, and well, the x component just doesn't exist, doesn't matter. The y component matters. Velocity points up because it's moving up. Acceleration points up because it's speeding up. So the equation number 1, m times a, is equal to tension minus the magnitude of the force of gravity. But for the second object, this set of axes is not the most convenient choice anymore. What is an axis? Again, it is just a ruler. We can place it any way we like, or we can imagine it any way we like. So we don't have to stick to the same set of rulers we use for one object. For another object, the most convenient choice looks like this. And as in the past, we could have called them what did we do? P and Q, for example. Why not? It's not X and Y anymore. Yeah, it's P and Q, T and R, V and W. So now, what does the Newton's second law tell us? Well, first of all, relative to the Q axis, we only have, again, the normal force and this component of the force of gravity, which we call perpendicular. And they must have exactly the same magnitude. They cancel each other out. So the normal force equals to mg times cosine of theta. That's theta. When there is no friction, normal force doesn't matter. Normal force only matters when friction is involved because friction is related to it. But if there is no friction, well, we don't even need this equation. We need another one relative to the p-axis. Again, this object travels down, that's velocity, and it is speeding up, so acceleration points in the same direction. So now, the big mass times acceleration, this variable a represents the magnitude of the acceleration, which is the same for both. And it has to be equal to, well, this is what we call mg parallel. And we should subtract tension. So mg sine theta. That's the first equation. That's the second equation. Two equations, two unknowns. The first unknown is the tension, which we should have solved for. The second unknown is the acceleration, which we also can calculate. Two equations, two unknowns. The rest is what? Math. Oh. Not math. Math. Mathematics. Any questions? That's how it's done. Physics, yeah. Very simple. One more example. I have a couple of more examples to go through. On Monday, we're going to have a review, prepared questions. Hopefully today, by the end of this class, and definitely on Friday, we're going to start a new topic, energy and stuff. So we have solved a problem related to object moved by an elevator. So now we're growing up, building up on that. Now a situation involves two objects in the same elevator. So please tell me what you think. If the acceleration of this elevator points up, the velocity, and these are the choices, definitely points up, definitely points down, and et cetera, et cetera. Lost and found always have something useful. So, soundproofing device. So, +68 plus 160. I see more people here. Who's the victim of the day? What do you think? What did you say? Absolutely right. Because we don't know if it's speeding up or slowing down. If you're starting the motion, you're on the first floor, you want to go to the third floor, you press the button. Your motion is upward because you're moving up, and you're speeding up. So the acceleration also points up. But when you're approaching the third floor, you're still moving up, but you're slowing down, and acceleration points down. So there is no exact relationship between direction of the velocity and the direction of acceleration. If acceleration points up, both choices could have been correct. We don't know. So there is no enough information, right? That's a great answer. Think about it. That's a review question. So it's basically a preview of what we should think about. When we talk about forces, the direction of the motion doesn't really matter. So what do we have here is a system, and we can solve several problems in one. The magnitude of the acceleration is given. If the acceleration points up, that's case number one. Or if the acceleration points down, that's the case number two. If we choose positive direction upward, we can immediately cover both cases if the y component of the acceleration chosen either positive or negative. If it's a plus, the acceleration, that's case number one, case A. If it's a minus, that means case number two, case B, acceleration points down. How many systems can we choose? Two objects. It doesn't matter if we move them horizontally, like two boxes on a table, or vertically, still the same number of systems, 1, 2, 3. We can choose a system like this, we can choose a system like that, and we can choose the system like this. So we can write 3 Newton's law. Two kilograms. There is normal force acting on it. That normal force provided by this surface, by the top surface of the magenta box. There is a force of gravity, 2 times 10, 20 newtons. And the acceleration, well, plus or minus 2 meters per second squared. Plus means we point it up, minus means we're pointing down. So the Newton's law immediately tells us 2 kilograms times a plus or a minus times 2 should be equal to the normal force. Normal force points up no matter what, minus 20 newtons, because force of gravity points down no matter what. And we can calculate the normal force in both situations. Normal force acting here. That's the force which we also could have called the force between the boxes. Yeah? This is the force acting from 1 on 2, which has the same magnitude as from 2 on 1, Newton's third law. And the next, the most convenient option would be to choose the whole system as one whole object. The total mass of that whole system now is 3 kilograms, but the reasoning is exactly the same. There is a force of gravity, mg, and there is another normal force different from the first one. That normal force provided by the floor of the elevator. But we can write the Newton's law and solve it if we want to. Any questions? Do I speak too fast? Do I speak too slow? Too loud? Too quiet? Moving on. Actually, I have a slide with answers. One more situation to discuss. I want to discuss it because it involves the change in the normal force and the friction at the same time. If we didn't have any friction involved, normal force wouldn't matter at all, and it wouldn't be any difference if we push or if we pull. But because there is some friction, and friction is related to the normal force, and the applied force changes the normal force relative to a horizontal situation. So how does it work out? Well, we can again consider, okay, solve both problems at once. So the only difference between pushing and pulling is the direction of the vertical component of the applied force. Again, There is force of gravity, no doubts. There is a normal force, no doubts. Now, friction. What kind of a friction is that? Static or kinetic? It's sliding, so kinetic. But we barely make it move, so we don't speed it up, we just slide it with constant velocity. So the acceleration has to be equal to 0, and that means net force acting on this piece of ice should be equal to 0. All forces should cancel each other out, and of course we can choose x and y axis and write two components of the Newton's law. But what I prefer is replacing the angled force with two forces which have magnitudes equal to the components of the applied force. That's it. So what do we have? Instead of this red arrow, now imagine it disappears, but instead of this red arrow, we now have one green arrow pointing to the right. And that's what we normally would have called the parallel component of the applied force. And there's another arrow which points straight down. And that's what we call perpendicular component of the applied force. Let's pause for the moment. Or, if we pull in, what does it change? Does it change the parallel component of the applied force? No. But the vertical, the perpendicular component of the applied force now points up. So the difference between this case A and this case B is the direction of this component. So if we choose positive direction upward, this component is negative relative to this axis, and this component is positive relative to the same axis. That's it. Well, geometry, of course, tells us how these components are related to the actual force. 90 degrees, 25, F. Well, we don't know it, but it doesn't matter, because when we solve a problem, when we write equations, when we analyze connections, it doesn't matter what we know or what we don't know. The connections don't depend on our knowledge about those connections. So we just write equations and believe they will be sufficient. That's it. We have to believe. So this is supposed to be equal to the magnitude of the applied force times cosine of this angle, theta 25. And that's supposed to be equal to the magnitude of the applied force times the sine of the same angle, theta 25. What? Sorry? Did I? I did it on purpose. You're watching. You're following. No, I didn't. So, if net force equals 0, what does it tell us? It tells us that, well, relative to the horizontal, relative to the x-axis, the frictional force must have exactly the same magnitude as this component of the applied force. Relative to the y-axis, relative to the vertical axis, vertical components, vertical forces. So what does it tell us? So, well, we have three vertical forces. Gravity definitely points down. Well, this is how I want to write it. The sum of all components is equal to 0. So this plus this, and now either a minus or a plus for this should be equal to 0. Minus means case A, plus means case B. So again, problem two problems in one. Two birds by one stone. Well, are we done? Well, we always should ask a question, have we exhausted all possible connections which might be important? In this situation, the answer is no. Friction is involved. Friction is important. So we must write a connection between the friction and, well, the normal force. So the magnitude of the force of friction also should be equal to the coefficient of friction times the normal force. And now we're done. With physics. What's left? Algebra. Algebra, algebra, algebra. You know, I know you love algebra, so that's why I'm not going to do it. I'm going to leave it for you. Two more situations I want to discuss, this one and one more. So this is a case when, again, we have two objects moving together, a coupled motion. Just to illustrate that it's nothing special, just this. We know what's happening when we just have a box and a string attached to it and we're pulling it. Gravity normal, applied, friction. Well, if we don't pull strong enough, static friction. If we pull strong enough, kinetic friction. What's happening now? Is it much different from this? Well, still I want to ask you a question. Start thinking. What force is the reason for this box to have acceleration? So it starts, you see, it moves faster and faster. So what is that force which is responsible for the acceleration of the top box? I'm going to switch to the projector, and I want to give you possible answers. Okay, first. Again, this is the situation. And this box has some acceleration. And the forces are tension, of course, gravity, normal, static friction, kinetic friction, hand, table, moon. I am tired. None. You can start pressing. Of the above. That's it. Yes.
Or what is the exact question we're answering?
What force is responsible for this acceleration? A. A is not zero. F net is equal to ma, so net force cannot be equal to zero, but what actual force is a part of that net force which kind of supplies that acceleration to this top box. All right. Survey says four is the most popular, and oops. 4 is the correct answer. Static friction. First of all, that's an elimination problem. That cannot be tension, because the string doesn't touch it. Gravity is perpendicular to the acceleration. Normal force is perpendicular to the acceleration. No hands. Well, this is just, well, I don't know, maybe this one. But still. So basically, you should choose between the static friction and kinetic friction. Is there a motion? Well, kind of, yeah, because motion is relative. It's always there. But when we talk about friction, we need to look at the motion of one object relative to another object. There is no relative motion. So if you forget about everything and look just here, this surface provides static friction to it. And that static friction makes it accelerate. Well, now, the rest is very obvious. We can again choose how many systems? 3. The whole, the top, the bottom. For each system, we can write the Newton's law and solve it. For example, for the whole system, here, force of kinetic friction, and the force of gravity acting on the whole system, and here the normal force acting from the tabletop on the lower box, and the acceleration points to the right, and positive x direction points to the right, positive y direction points up. M plus little m times A has to be equal to the applied force minus frictional force, which equals to kinetic friction times normal force. And normal force has the same magnitude as total force of gravity. How would I write the Newton's law for, well, this is the x component of the Newton's law. Yeah. This is basically the y component of the Newton's law. How would I write the law just for the top box, for the small one? Well, relative to the x-axis, there's only one force, horizontal force acting on it. That's a force of static friction, and that has to be equal to little m times the same acceleration. Well, thank you. Same time, same place on Friday. Actually, I have slides with solution also. So if you're interested, you can finish the work at home. All right, thank you very much. We're done for now. Closing this. Closing this. Yes, sign-in sheet is over there, I think. That person. Yeah, you can take down this. Yes,
Could you send this to me? I just need to switch sections.
yes, just a minute.
Yeah, of course.
Okay,
Just sign right there. I'm just switching to a different timer now.
that's fine.
Awesome.
Yeah.
Thank you.
Okay, thanks.
Sir, I was a little confused about what you said about the lab. So if we miss lab this week, it will just get pushed to next week. We'll have lab 2 next week for the Tuesday labs.
If your regular lab time is on Tuesday, your lab will be next Tuesday. That's it. That's it.
Hi, I'm
Yes.
on the track team, and we're traveling this Friday to go to conference championships.
This Friday is just regular Friday.
I was just wondering if I could, should I email you about getting my discussion section?
You should send me an email
Okay.
related to everything, you know, and maybe a copy of this just in case. Just scan it.
All right. Thank you.
Yes.
Should I have you sign something on that?
Depends.
It's for transfer school. I just need the signature.
Where?
I will fill in the rest of it.
Again, where? Have it checked.
I don't know. It says grade.
Well, right now, everybody has an A. After the exam, that could have changed, but
Yeah. It's just my parents are moving, so I can't stay here.
yeah. All right. That's it.